Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the force acting on a current carrying wire which is placed in magnetic field. So you can see that this is a current carrying wire and this wire is placed in a magnetic field, and you can see that the shape of this wire is arbitrary. It does not have any regular shape and some current is flowing through this wire. So if we wish to find out the force acting on the small element, a small length of this wire, this length is dl, then this force acting can be calculated by a simple analogy in which we assume that a charge q or a charge dq, small charge dq, is flowing in the direction of dl, and it moves by a distance of dl in time dt. So the velocity v of this charge will be dl by dt. Okay, and we know that the force acting on a moving charge in the magnetic field df is qvb. So q in this case is dq and velocity is v cross b if we write down it in vector form. So df will be equal to dq into v, which is dl by dt cross b, and dq by dt can be written as I, so it would be I L cross b. So this is the force acting on a small current carrying wire which is of a length dl. Okay, and the direction of this force, now as first of all let us discuss that this force is governed by the cross product of dl and b. So you can see that dl is, what is dl? Now dl is the length of, we can say that small length of wire, and or we can write it down as small length vector, small length vector of wire pointing in the direction of current. Okay, so dl vector is a small length vector of wire which is pointing in the direction of current. Now if we find out the direction of df, then we can say that due to the fact that f is represented by the cross product of dl and b, so we can say that the direction of f would be in the plane perpendicular to dl and b. So you can see that this dl and b are in this plane of the screen, and therefore the direction of f would be inside the plane or outside the plane. Specifically in this case, if we see the sequence of dl and b, so we can see that dl is written before b, so dl cross b will be pointing inside the plane. You can rotate the fingers of your right hand from dl to b like that. So fingers would be rotating in clockwise sense and the thumb would be pointing inside the plane. So the direction of df would be inside the plane. Okay, so this is the force acting on this small current carrying wire, and if we wish to find out the force acting on the complete wire of arbitrary shape, then obviously we have to integrate the total that small force. So f would be equal to the integration of df vector. Now you know that the integration is the continuous addition. So if obviously, and we also know that df is also a vector quantity because force is a vector quantity, so df is vector quantity, and integration of df vector represents the fact that we are adding the vector, we are doing the vector addition of the small forces acting on each small length of the wire. And we know that if we add up all the small length of the wire dl, then the vector sum would be the shortest length between the two ends of the wire. So directly we can say that f will be integration of df is I dl cross b, and in this f can be written as I integration dl and cross with b. So in this case you can see that this is vector sum of all the small elements, and therefore the vector sum of all the small elements would be the direct shortest distance or shortest length between the two ends of the wire. So f vector will be equal to I lab vector cross b, and lab vector is the length vector which is formed by connecting the ends of the wire directly, and the direction of the length vector lab is in the direction of current, which means that we know that if direction of current is from A to B in this case, then this length vector would be pointing from A to B. And if obviously this is a current carrying loop of any shape, arbitrary shape, this is a arbitrary shaped loop, and the magnetic field is like that. So the vector sum of forces on the loop will be 0, and obviously the magnetic field should be uniform. So this formula is valid only when the magnetic field is uniform, and for a current carrying loop of any shape, the vector sum of net force would be 0. So this is the analogy of this force acting on a small current carrying wire, and we can also find out the force acting on the large current carrying wires by taking the shortest length between their two ends, and the length vector should be pointing in the direction of current flowing. Thank you.